Hello, and welcome to Chapter 5 of Introduction to Statistics, the Think and Do book. Today we're going to cover Chapter 5.1. Just kidding. Haha, you gotta admit, that was a pretty good Scott Stevens impression. Okay, so let's talk about today's video, which is going to be on Section 5.1. Which is called Discrete Random Variables and Probability Distributions. So, a couple things to take down here, some definitions. One, we're going to be talking about these things called random variables. And a random variable is a variable. It's basically just something that can change, something that can obtain several different values. We typically denote variables with some variable like x. And it's just going to be something that has some numerical value. And it can be determined by chance or by some outcome of a procedure. So this section we're going to be talking about these things called discrete random variables. Discrete means it has a finite or countable number of values. So for example, the number of heads in 3 tosses of a coin would be finite or countable because the answer would be 0, 1, 2, or 3. Opposed to continuous random variables, which we're not going to study this chapter, but we'll study in Chapter 6, are variables that can have infinitely many values, and they can be measured on a continuous scale without gaps or interruptions. So things like this are things like weight. The reason why this is continuous is because I could weigh 180 pounds, or I could weigh 181 pounds, and I could also weigh any amount between those two values. Like I could weigh 180.5, or 180.273, or 180.2735678, whatever. You can actually obtain those kind of values, as opposed to this example back here with the tosses of a coin. You can't get like 2.3 heads when you toss a coin. There are gaps between the values, and that's what makes something a discrete random variable as opposed to a continuous random variable. Alright, so we're going to take a look at these things today called probability distributions, which are basically little tables that talk about all the values in a discrete random variable and all the probabilities associated with it. So let's take a look right down here to example 1. This is our first discrete probability distribution. So what we have is the example we referred to earlier, the number of heads that come up when you flip a coin. And those possibilities, you could get no heads, which would be if you get all tails. You could possibly get 1 head. You could possibly get 2 heads. Or you could possibly get all 3 of them being heads. And as you guys saw in the group work we did last class, when you make those tree diagrams, you can actually find the probabilities associated with each of those outcomes. And they are right here. So this thing right here all together is a probability distribution. It has all of your potential outcomes. I don't know what the heck I just did there. And all of the probabilities associated with each specific outcome. Okay. So 2 things that have to be true for a probability distribution, and these should make sense. One is that the sum of all of your probabilities must equal 1. So when you add up all of these probabilities right here, you're always going to they're always going to add up to 1. That if they don't add up to 1, that means basically you left out some possible value in your table. And also that all of the probabilities in this table all will be between 0 and 1. And that should be for pretty obvious reasons, like we talked about in the group work in sections 4.1 and 4.3, because any probability always has to be between 0 and 1. Okay. So right here it says verify that example 1 represents a probability distribution. So you can see, do these 4 probabilities all add up to 1? Well, you can take out your calculator and check that yourself. And you'll find out that indeed they do all add up to 1. And are all of these probabilities all in between 0 and 1? Yeah, sure they are. So that means we do have a valid probability distribution here. Okay, so one of the main things in this lesson is to calculate the mean of a discrete probability distribution. So the mean of a probability distribution is really just a weighted average of these x values. Okay, so we have a little formula here that mu is the sum of your x values times their associated p of x values. So basically the values and each value's corresponding probability. Okay, so let's use the table in example 1 to calculate the mean number of heads in 3 flips of a coin using this equation we just learned. Okay, so we have our table here. I'm going to erase all of this work here if possible. This isn't going so well, but hopefully it'll eventually erase. Yeah, it's not going so well at all. Okay, whatever. Let's just, oh, and it's gone. How about that? Okay, so what we need to do is we need to take the sum of all of our x times p of x's. So I like to make another column here. We'll call it x times p of x. And let's find all those products. So 0 times 0.125 is 0. 1 times 0.375 is just 0.375. 2 times 0.375 is, take out your calculator to figure that one out, it should be 0.75. And 3 times 0.125, again, if you take your calculator out, you'll find that is 0.375. So, and then the way we get our sum of a probability distribution, the mean of the probability distribution, is by taking the sum of all those x times p of x values. So all these x times p of x's, we take the sum of them, and that ends up equaling 1.5. So there you have it. That's the mean of the probability distribution. It's 1.5. All right, and for a round-off rule for these, the textbook gives us this round-off rule that when you calculate the mean of a probability distribution, round the final answer to one more decimal place than the x values. Okay, so that's it's very consistent with the round-off rule that we've learned already in class, and it's just being more specific to go one more decimal place than the x values. Cool. All right, so the next thing we're going to talk about is called expected value of a random variable. The expected value is a phrase that's used quite a bit in statistics, and basically all it means is it's the mean of the probability distribution. So you'll see here in this box we have expected value, and it's denoted with E. Another thing, you'll also see it denoted as EV for expected value, and it's the same exact formula as the mean. It's just the sum of your x values times their corresponding p of x. Okay, and expected value comes into play a lot. One really emerging career in the world of statistics is this thing called an actuary. You can Google that if you're interested. And basically it's someone who calculates a lot of expected values of things occurring, specifically for like insurance companies and stuff. So let's go on to example 2, which is this lottery example. So I buy one of 200 raffle tickets for $10. The sponsors then randomly select one of the tickets. If they pick mine, the sponsors give me $100. Otherwise, I get nothing. What is the expected value of this raffle to me? So what expected value tries to capture is the average outcome. Because if you think about it, what's going to happen in this raffle? Either you're going to win $100 or you're not going to win anything. It's one of those situations. It's nothing in between. So what we're trying to do is trying to capture like the average overall essence of what the average raffle ticket sucker, raffle ticket buyer is going to end up with. So the way we do that is we calculate the mean of this probability distribution. So in this situation, there are two outcomes. And this is the first thing you always want to do is list your outcomes. So the two outcomes in terms of the scenario are you either win or you lose. And what are the values associated with those outcomes? And I like to put those in a separate column. So if you win, well, you win $100, but you also paid $10 to buy the ticket in the first place. And for any of you who have ever entered a raffle, when you win a raffle, do you ever get your money back at the end? No, the sponsors keep that money. So you win 100, but you paid 10, so your net outcome is $90. And what's the value associated with not winning? Well, if you lose, then you just lose your $10. So your net outcome is negative $10. Okay. Now let's talk about the probabilities associated with each outcome. Well, there are 200 raffle tickets, and the sponsors randomly select one of the tickets as a winner. So what's the probability of winning? It's 1 out of 200. You can leave that in fraction form, or you can put it in decimal form if you'd like. And what's the probability of not winning? Well, if only one ticket wins out of 200, then that means 199 tickets are all losers. So the probability of not winning is 199 out of 200, and you can leave that as a fraction or a decimal. And this right here is basically your probability distribution. Okay, and now our goal is to find the mean of this, which we know is the sum of our x's times our p of x's. So we multiply our x 90 times our p of x, and we get 0.45. Then we multiply this x of negative 10 times this p of x of 0.995, and we get negative 9.95. And to find the overall answer, we take the sum of those x times p of x's. So add these two babies up, and you get an expected value of negative 9.5. Okay, so what does this expected value of negative 9.5 mean? It means that the expected value is negative 9.5. So if you were to play this game many times, like if you were to buy all of the tickets in this raffle, then you would average a loss of $9.50 per ticket you purchased. Okay? And the author mentions this another viewpoint here, which I am not very fond of, so I would ignore that. Okay. So why don't you guys pause the video and try this your turn example, and then when you press play, I'll go through my solution and you can see if yours matched up. Okay, so we play a $5 carnival game where you fish for prizes. There are 100 plastic fish circulating in the pond. Each fish contains a small piece of paper with a prize code printed on it. There are 10 red fish with a $10 prize, 20 blue fish with a $5 prize, 30 green fish with a $2 prize, and 40 orange fish with a $1 prize. You pay $5, drop your line, and hope for the best. What is the expected value of this game to you? So first, what are all the outcomes? Well, you could end up with a red fish. Bear with me while I learn how to write with my mouse. You could also get a blue fish, or you could get a green fish, or you could get a orange fish. This is not working out very well. Okay. So what is the value associated with each of these outcomes? Well, if you get a red fish, then that comes with a $10 prize. But you paid $5 to play this game to begin with. So what is your net outcome? Your net value here is going to be you have netted $5. What about for a blue fish? Well, you win a $5 prize for getting one of the blue fish, but you also paid $5 to play the game to begin with, so your net outcome is nothing. And what about green fish? For green fish, you win a $2 prize, but you paid $5 to play to begin with, so you end up with $3 less than you started with, so we'll denote that as -3. And for the orange fish, you can win a $1 prize, but again, you paid $5 to start, so your net outcome is -$4. Okay, so let's figure out what the probabilities of each of these occurring are. So the probability of getting a red fish, there are 10 red fish out of a total of 100 fish, so that means the probability is 10 out of 100. What's the probability of getting a blue fish? Well, there are 20 blue fish out of 100, so the probability is 20 out of 100. And you could put these as decimals if you like, or you can leave them as fractions. I tend to like fractions a little more sometimes. For green fish, there were 30 total out of 100. And for orange fish, we had 40 of them in the pond out of 100 total fish. Cool, so now we have our probabilities. And now we need to find our x times p of x's, and then we want to sum them all up. So 5 times 10 out of 100 is going to be 50 out of 100, or 0.5. For the blue fish, you don't get anything, so 0 times 20 out of 100 is just 0. For the green fish, we have -3 times 30 over 100. That's going to be -0.9. And for the orange fish, you get -4 value with a probability of 40 out of 100. So you multiply those and you'll get -1.6. Okay? So when we sum all these up, sum up all of our x times p of x's, we end up with, let's see, -2. -2.0. So that means your expected value in playing this game is -2, or you would expect that you're going to lose $2 from playing this game. The author has a bit of a cynical perspective on this, and he says you take your nephew to the carnival and he wants to play this game. Instead of paying the $5 for him to play, you offer him cash instead. What is a fair cash settlement? Not so fun, kind of taking the joy out of the carnival game for your little nephew. But there is some mathematical accuracy to the statement, so it's kind of an interesting way to look at it, but maybe not the funnest way to look at it. Alright, so that'll do it for this video. Hope you enjoyed, and I will see you guys in class.